Hi, this program will take a look at the bonding triangle. It's a tool that can be used to determine the type of bonds that are present in binary compounds. So let's look at some of its features. You see the triangle here within three axes. One that looks at the difference in electronegativity, the other axis the average electronegativity, and you may have a third axis the percent covalent nature of the bond. I want to begin in the bottom left corner. By being metallic, they have low electronegativities, hence a low average electronegativity, and very little difference between them. My example here is a strontium and magnesium complex. We can see here the average is about 1.1 and the difference here about 0.3. In the bottom right-hand corner, we have covalent compounds. They have high electronegativities. These would be nonmetals, and very little difference between their electronegativities. My example here, chlorine gas. At the top of our triangle, we have ionic species. They have a moderate average electronegativity. That occurs because we have a metal usually combining with a nonmetal, something with a low electronegativity pairing with something with a high electronegativity. Hence, we're calling them moderate averages. However, there is a high difference between their electronegativities. And my example here is sodium oxide. Here we can see the average lies somewhere around 2.2 and the difference about 2.5. My last example lies in the polar covalent region, which lies between ionic and covalent. These have moderate electronegativities and moderate differences in their electronegativity. My example here being water. So the average here is about 2.6 and the difference about 1.3. Let's take a look at a problem that would involve our use of the triangle. Here we're asked to predict the bonding type and percent covalent nature present in aluminum bromide. At first glance, aluminum being a metal and bromine being a nonmetal, we would probably expect an ionic bond. But let's look more closely at their electronegativities. Their average electronegativity is about 2.3, which puts them on this line. Secondly, the difference in their electronegativities is about 1.4, putting them on this line. Where they intersect, I can see they lie in the polar covalent region. Hence, that would be the major bonding type. As far as the percent covalent nature of the bond, it reads about 60% on that axis. So there's a quick look at the application of the bonding triangle.